Hi everyone, this is Taqi from the University of Arizona. Today I will present my work that enables low latency 4G LTE data access through edge computing. First, I would like to introduce LTE Background. 4G LTE has three components, as you can see in the figure: the device, radio network, and the evolved packet core. The device camps with a radio network that connects with the core network. The core network has a controller known as MME and HSS that holds the records of LTE subscriber. The serving gateway and the PDN gateway are the two data forwarding planes in the EPC. LTE performs control plane and data plane operation. Control plane logic performs device registration, deregistration, mobility, location update, and many other control plane procedures. Whereas the data plane or the user plane forwards the traffic to the next hop along the path to the selected destination network according to the control plane logic. First, I would like to introduce the IP multimedia subsystem or IMS, as we take it as a use case example in this work. So you can see that the IMS acts as an overlay on 4G LTE network. It implements a number of functional modules such as proxy server, serving server, and the media server. IMS signaling or the IMS control plane carries wise multimedia control plane traffic, whereas multimedia data traffic connects telephony network with the 4G LTE through IMS media server. Here, we should note that the regular data traffic, such as web traffic, directly goes from LTE PDN gateway to the internet and does not involve IMS. So today, both EPC network functions and the IMS network functions are implemented over purpose-built hardware platforms. The examples include Ericsson Blade System or EBS, and Alcatel-Lucent's Element Management System or EMS. These purpose-built platforms has a number of advantages. They provide strong coupling between the hardware and the software and provide guarantees on high availability and low latency data access. They can do so because they provide dedicated network resources to every user. Now, the LTE network function virtualization is an emerging concept in 4G LTE that moves away from proprietary solution and instead use off-the-shelf hardware to implement LTE core network functionality. It reduces both capital and operational expenditure. As you can see in this example, LTE network elements are moved to the cloud or virtualized EPC network function. Now, the operator network only keeps the management-related interfaces to forward the network traffic from LTE users to an appropriate virtualized EPC network function. In this work, we argue that the existing approaches to LTE NFE are bad. Although control plane signaling messages are executed on the cloud, which is good, however, the user plane traffic is unnecessarily forwarded to the virtualized EPC gateway, that is serving gateway, PDN gateway, IMS network function, before this traffic reaches to the internet. Consider the voice traffic which always traverses through the EPC data center before it arrives the destination device. Such an implementation choice brings data latency. So this is an example where all the traffic is going from the device to the operator network to the data center and then coming back to the device. Mobile edge compute concept addresses the shortcoming in LTE NFV implementation by decoupling control plane and data plane. The control plane traffic still goes to the data center, whereas the user plane traffic is routed through the mobile edge compute service installed at the operator network or at the edge of the network. We decompose serving gateway and the PDN gateway user plane functionalities and install them at the edge. We also install a media gateway of the IMS to the edge. As you can see that all the traffic now goes from the edge to the internet without going to the LTE PC data center. So in this slide, we provide more details exactly what functionality of the LTE PC forwarding plane network functions are put at the edge and what functions are placed at the core. Now in our design, we place all the control plane functions at the data center while moved all the forwarding plane logic at the edge. We face another problem because in our implementation, we find that the latencies are still increased when the control plane and data plane traffic share some dependencies. We take an example of a data charging control plane module, which is placed at the data center. To charge the data packets, all the traffic unnecessarily needs to go to the data center first before it is sent to the device. To address this issue, our idea is to provide the copy of all those network functions to which the data traffic has dependencies. So we move the charging function to the edge too. So our design considerations include that we share the common functions between the control plane and the user plane. So these functions include the charging function or the PCRF, which both the control plane and the user plane rely should be shared. That means that they are copied at both control plane, that is at the data center and at the edge, which is implementing the data plane. Now let the control plane, in our idea, we want to let the control plane being the central entity handle the network function allocation. So here we show that in this implementation, we find another type of a problem which introduces the race condition. So consider this example. So say there is a location update procedure, which is known as a tracking area update procedure, is ongoing between the device and the controller, MME. Now, while this tracking area update procedure is ongoing, the serving gateway user plane is overloaded. And it requests the serving gateway control plane to allocate another instance. Now, at the same time, the relocation request procedure, which is a part of a tracking area update procedure, kicks in. So in other words, these two relocation requests have race condition to each other. So to address this, we let the user plane manage its own resources based on the policy provided by the control plane. So we also find that there are the issues related to deadlock as well. So consider an example, again, the tracking area update procedure. So device generates a tracking area update procedure by sending a tracking area update request message to the controller or MME. MME exchange internal signaling message with the P gateway control plane at the PCRF or the charging function of the control plane. And it locks the module because it needs to reflect the updated position to the PCRF user plane. Now, assume that there's an overload happening at the P gateway user plane. Now, the P gateway user plane also exchanging internal signaling messages. And it also lock its charging module at the data forwarding part. So now both PCRF-U and PCRF-C have locked each other, locked their own modules. But they want to reflect their changes to each other as well. It means that they are locking each other resources, and now it introduces the deadlock scenario. So to address this, we propose to use the blocking mode operations. Now, we explain our concept of FERRET, which we propose in this paper. We take, again, we take an example of IIMS and we implement over mobile edge compute. So the key idea is that the voice over LTE procedure or any multimedia procedure has basically two types of phases. The first phase is the call establishment phase, which is pure control plane, and the second phase is related to the data packet flow, which is the part of the user plane. Now, our key idea is that that all the control plane procedure should be exchanged at the control plane or at the data center or the virtualized EPC. So let's say network function 2 send a message to network function 1, which is message M1. At the same time, we record it in a memory, this exchange of messages. And again, NF1, network function 1 send a message to network function 2, which is M2 message. We again record it. And once all the control plane procedure concludes at the data center, then we flush this control plane operation at the edge. So in this way, we do not let the user plane interfere the control plane procedure which are happening while the call is being established or while the multimedia packets are being established. So we implement it, and we found that our approach significantly reduces the latencies. So here you can see that the baseline approach, where we do not have the implementation does not have the mobile edge compute. The traffic goes to the base station, which is either to the virtualized EPC, and then it goes to IIMS. So this whole path takes a lot of latencies up to the order of 110, roughly 110 milliseconds. Whereas in our approach, where all the implementation, all the forwarding plane is handled by the edge, our latencies is roughly around 25 milliseconds. So to conclude, we find that mobile edge compute, which is a part of 5G agenda that requires important network components to be installed at the edge. And we take a use case example of IMS, and we demonstrate that MEC architecture that reduces up to 6x user plane latencies compared to the baseline approach. And in the future, we will measure the MEC design from different system and network aspects. We will consider bandwidth, latency, call rate, mobility, and other LTE procedures as well. So with this, I will conclude my talk, and I would like to get your question. Thank you for your attention.